This is lesson 5.2, Extreme Value Theorem, Global versus Local Extrema, and Critical Points. So the Extreme Value Theorem says if a function f is continuous over the interval a, b, then f has at least one minimum value and at least one maximum value on the interval a, b. So right here, if we look at this definition, we see we're talking about minimum values and maximum values. And when we studied pre-calc and we looked at polynomials, we learned that minimums and maximums, this is the same as extrema, right? Those are saying the same thing. And remember, we learned that these are like hills or valleys. So top of the hill, bottom of the valley. All right. Your hills are your maximum values. Your valleys are the minimum values. And right here, this term global versus local, or this term absolute versus relative, those are actually saying the same thing. So I want you to keep in mind that if you see global or absolute, those mean the same thing. If you see local or relative, those mean the same thing. Global and absolute, those are talking about the highest point and the lowest points on the graph. So the absolute highest hill or the absolute lowest valley. These, local and relative, these are talking about any hill, any valley. They're still maximums, they're still minimums, but they're not necessarily the highest or the lowest. All right, so if we look at this picture on the right, we can go along our curve and we can identify where all these points are. So a couple things. First of all, there's some controversy around the endpoints of a function. So we're actually going to save those for last. The other thing is we only look at defined function values. So I don't care about these holes in the graph. Those are undefined. I only care about these filled in circles. Those are the defined points. All right, very good. If I follow along the curve, it looks like I have a top of the hill right here at this defined point. And the way I know that it must be a maximum is if I were to pretend for a minute to take a small interval around that point, I would look to the left of that interval and the right of that interval, and I would see where my function is. So if I'm looking at this point, to the left, all of my function values are lower, and to the right, all of my function values are also lower. So this must be the high point. So this is a maximum value. And if you were to imagine for a sec that we actually draw a straight line across the graph through that point, we can see that it is the highest point of the entire function. So this is the absolute maximum. And I'm going to put ABS for short. Okay, continuing along, looks like we have another defined point right here. So once again, if I imagine for a sec that I look to the left and the right of that point, all of the function values on the left are higher. All of the function values on the right are also higher. So this must be a low point. This is a minimum. And we would say this one is a local minimum because it is not the lowest point on our graph. All right, following along again, we have another point right here. All right, so if I, again, take an interval, I'm going to look to the left and to the right, and I'm going to see that the function on the left and the right is higher than this point. So this must also be a local minimum. And then it's not really marked for you, but there also looks like there should be a point right around there that if we were to look to the left and the right of, I can see the function on the left and the right is higher than that point. So this must also be a local minimum. Okay, so be careful. Even though this part of the curve looks like it's a hill and not a valley, because this point, this defined point, sits lower than the rest of my curve, it's actually a minimum value. Okay, now the endpoints, let's talk about those briefly. There is some controversy here. If I look to the, let's do this right endpoint first. If I look to the left, it looks like my function is lower. However, there's nothing going on the right. So I normally need two things to compare to the point in order to make a conclusion. So some people say that this is, and I'll put it in parentheses because it's we can't conclude it, but some people say this is a local max because the function to the left is lower than that point. But other people are going to tell you that that is neither a maximum or a minimum value because there's nothing on the right side to compare it to. So whatever you decide, however you want to interpret it, I'll be fine either way. I just want you to know some people, in fact, it's about 50-50. Some people are going to tell you that that is a maximum. Some people are going to tell you it's nothing. Same thing here. Some people are going to say this one on this left endpoint is a local minimum. Other people are going to say it's nothing. All right, very good. Let's look at two more problems. So it says in the examples below, find all extreme values, identify the type, and where they occur. And in this example, I'm actually going to leave off the endpoints. We're just going to look at the function between the two endpoints. So if I start following along this curve from left to right, right here, this looks like I have a maximum value. And remember, if you were to draw a flat line through it, we can see that that point is the absolute highest on the graph. So I could say I have an absolute maximum, and I have to give a value to it. So we're going to look at the y value of that point. So this is an absolute maximum of the y value is 5. And then you have to give a location. So I know that this is at x equals 0. It's right on the axis. All right, I'm going to keep going. This point is undefined, so I'm going to jump down to this one. And if I look at this point right here, to the right, my function is higher. To the left, my function is higher. This must be a low point. So I can say I have a local minimum. And the value of this point is 2, so of 2. At, and then its location looks like x equals 1. And that's it for that one because this one right here is an endpoint and it's undefined, so I'm going to ignore it. All right, same thing here. We start with an endpoint and it's undefined, so I'm going to ignore it. Some people might be tempted to think this is either a maximum or a minimum value, and I can see why. However, once again, look to the left and look to the right. So on the left, the function is lower. On the right, the function is higher. So this is nothing. We're going to keep going. This looks like a maximum. And once again, if I were to draw that flat line straight across and through that point, I can see it's the highest point of the graph. So I have an absolute maximum. The value of that point is 3. And it is at the location x equals -1. All right, keep going along the curve. This one's undefined, so I'm going to jump up here. The right of the function is lower. The left of the function is also lower. So we would say this is a high point. So this is a relative or local max of the value is 1 at x equals 1. And then once again, we get to the end and it's an endpoint. So for this problem, I'm going to leave it off. Right now, if we look at the next problem, it says find all extreme values, this time justify why they are extreme values. So it's a little trickier, but first of all, I can go through the curve and I can say, okay, this looks like a max, This looks like a min. This looks like another max. We have another minimum, and this is one last maximum point. And I have to go through each one and tell why it is an extreme value, why it's a max or why it's a min. All right, so that actually has to do with the derivative. So if I were to take the derivative of this first part of the function right here, I would get a positive number because the function is going up. The slope is positive. If I were to then look to the other side of this point and take the derivative here, I'd get a negative number. The graph is going down. So if I go from positive to negative, in other words, increasing to decreasing, that means at some point I must have turned around, and that turnaround is at the top of a hill. So this is a maximum point. Even more so, what I want you all to realize is if you were to take the derivative at that point, so imagine a tangent line for a sec, the derivative of this flat line would be 0. So the reason I know that this is an extreme value is because the derivative is 0. And it's actually the same reason for maximum values and minimum values. If you were to take the tangent through this point, the derivative is also 0. Same thing here. Same thing here. And then this one's a little weird. We have a sharp corner. These are nice smooth curves, but this is a sharp corner. And if you remember from last semester, you cannot take the derivative of a sharp corner. So in this one, the derivative does not exist. All right, so there really is no, if you're just taking the derivative, there's no way to tell the difference between a maximum value and a minimum value. They both have the same slope of 0 or the same derivative of 0. And so this actually brings us to our definition of a critical point. A critical point is just a potential location for a maximum and a minimum value. So if I take the derivative and I figure out all the points where the derivative is 0, there's nothing distinguishing or telling me the difference between a maximum and a minimum. I just know that they are potential locations for either one of those. So how do I find a critical point? So there's two ways to do it. In order to find all those points where there might be a maximum or a minimum, I have to first figure out the derivative and figure out where it's equal to 0 and then where it does not exist. All right, let's look at two problems to show this point. So problem 3, it says find all critical points of the function f of x is equal to 1/3 x cubed minus 9x plus 24. So once again, if I'm going to find critical points, I first need to take the derivative. The derivative of this function is x squared minus 9. And first of all, I need to ask myself, are there any points along this new function? So are there any points in the derivative where the function is undefined or where the derivative doesn't exist? And I know that no, that's not true because x squared is a polynomial function. It's a quadratic, so it's a parabola. And parabolas are continuous everywhere. So there is no point where the derivative does not exist. But there are points, in fact there's two of them, where the derivative is equal to 0. So I can figure that out. I can set x squared minus 9 equal to 0. I can solve for x, and that's going to tell me where those potential locations for maximum and minimum values are. All right, so when I do this, when I solve, first I'm going to bring that 9 over to the other side. Then I'm going to take the square root of both sides. Now when you take the square root of 9, be careful. It could be positive 3. It could also be negative 3. So if I'm talking about my critical points here, there are two of them. One at x equals 3 and one at x equals negative 3. All right, in problem number 4, we have g of x is equal to 1 divided by the square root of 4 minus x squared. Now, before I take the derivative of this, when you take the derivative, you could do quotient rule. So low times the derivative of the top, so low d high minus high d low all over low squared. Or we can rewrite this first as 1 over 4 minus x squared to the 1/2 power. Because remember, the power of 1/2 is the same as a square root. And then I still have a fraction here, so I can rewrite it one last time. If I bring this whole denominator into the numerator, remember if I make it cross sides like that, the exponent is going to change signs. So this is also equal to 4 minus x squared to the negative 1/2 power. And that's something I can take the derivative of. So g prime of x is equal to, I'm going to bring that negative 1/2 out front. And then the exponent is going to be negative 1/2 minus 1, so this is negative 3/2. And then remember, I have derivative of the outside times derivative of the inside. There's some chain rule going on here because there's lots of stuff inside. So I need to take the derivative of this. That is negative 2x. And then I'm done. I could simplify it, clean it up a bit. Negative 1/2 times negative 2. The negatives cancel, and then I'm left with a half times 2, so that's just 1. So I have 4 minus x squared to the negative 3/2 power, and then that is going to be times x. All right, one last thing to simplify a little bit. This negative exponent, we can get this to cross back into the denominator and get the exponent to change signs. So this is x over 4 minus x squared to the, now it's positive 3/2 power, because when we moved this back into the denominator, the exponent had to change its sign. All right, now I'm going to look to see, first, are there any points where this function, this derivative, is undefined? All right, well, this is a rational function. It looks like a fraction. I know that fractions are undefined when their denominators are equal to 0. So first I'm going to take the denominator, 4 minus x squared to the 3/2 power. And I'm going to set it equal to 0. All right. First thing I'm going to do is I'm going to rewrite this, because 3/2 power, this is the same as the square root of 4 minus x squared, and then that is cubed. So these two are saying the same thing. If I square both sides to get rid of that square root, I end up with 4 minus x squared to the 3rd power. And then squaring 0, I still get 0. Then I can take the cube root of both sides and get rid of that 3. So we have 4 minus x squared is equal to, the cube root of 0 is still 0. So I'm left with this. I can get that x squared over to the other side. And then same thing as before, I could take the square root, and I should get x is equal to either positive 2 or negative 2. All right, now it looks like these two might be potential areas for a minimum or a maximum value. However, if you were to take 2 and plug it back into the original function, right? So we can do that off to the side maybe. We can figure out real quick, well, what is g of 2? Well, that's 1 over 4 minus 2 squared, and then I'm going to take the square root of that. 2 squared is 4, 4 minus 4 is 0, the square root of 0 is 0, so I end up with 1 over 0, which is infinity. All right, so at x equals 2, and in fact also at x equals -2, my function is undefined. All right? And remember, when we're talking about minimum and maximum values, we only look at defined points. So this is actually not true. Those two could have been critical points, but they're undefined. So we've done that. The other thing we got to do is we got to figure out, is there anywhere where this function right here is equal to 0? Well, yeah. A fraction can only be equal to 0 if the numerator was equal to 0. So x must be 0. This is our only critical point.